Okay, good morning. So I had posted a simple assignment for you to watch the videos related to module 7 and make a statement that you have done so. This morning, 10 people had submitted, 8 people still haven't. I, I think by mistake, I set it for Sunday night. I meant to do it for Monday night. So now I have set it to Wednesday night. That is by midnight on Wednesday, you should have completed this. This is again important for you to understand module 7 as well as score 5 points for watching through the videos and making a statement that you have done that. Okay. So if you have not already done, please do that. Don't lose out on those 5 points. Okay. I hope that's clear. You have time until Wednesday, but I would like you to do it today and get it done with. All right. So today is effectively our last discussion of topics. On Thursday, I plan to go over the mock exam 3 to solve it in step by step and then discuss it with you. So today I want to address the most important topic in this course, although we get to spend only one lecture on that, flow losses. So when I say flow losses, what I imply is if you have a pipe flow, what we have seen so far is if there is an entrance to the flow or entrance to the pipe, there is a certain section which we call, what do we call it? We call it the entrance length. Entrance length. And what is the characteristic of entrance length? What's happening during that phase? The flow profile is initially uniform. It enters a pipe. It has a certain developing zone. What happens in that zone? It progressively becomes more viscous. Very nice. Progressively becomes more viscous. And once it has become fully viscous, it develops a velocity profile which looks parabolic. Okay, and this velocity profile is what we call the fully developed flow. And this velocity profile has a form U of r equal to V central line times 1 minus r squared over r squared. And the derivation was also part of what you saw in the videos. For fully developed pipe flow, the relation between flow rate and pressure drop is known to be Q equal to pi over 128 mu, where mu is the viscosity of the fluid, times delta P over L times diameter to the fourth power. And Q, the flow rate, Q may be expressed as the average velocity, we call it V bar, multiplied by the cross section area. So in our case, V bar times pi by 4 d squared. Okay, so if you use this average velocity for the flow rate, we can write this V bar times pi by 4 d squared equal to pi over 128 mu delta P over L times d to the fourth. And this derivation, again, something that I ask you to watch in the recorded lectures. I need this relation to make a point, so just stick with me here. So this is pi, this is 32, okay? So we have p squared delta p over L equal to delta p over L equal to um, delta p over L times d squared equal to 32 v bar times mu. Hold on. And this rewrite this v bar equal to 1 over 32 mu times delta p over L squared times d squared. So I'm going to rewrite this delta p over L equal to 32 mu times v bar divided by d squared. Now, when you have a pipe flow over a certain length, this is our L, and we assume that the velocity profile is fully developed. Okay. The pressure drop delta P across this length, the pressure drop across a length L of piping scales with what you see from here, delta P scales with the velocity, that is the flow velocity, and what is the primary driver of this pressure drop? Why is the pressure dropping? Because of the flow happening. What is causing the pressure drop? What is causing this the pressure at this section P1? We call this P2. Obviously, P2 is less than P1, right? That's what pressure drop means. It drops in the direction of the flow. Why would it drop? We talked about this. What is the primary mechanism that leads to pressure dropping along the length of the flow? Friction, right? The pressure drops across the length, and the primary mechanism is friction due to fluid viscosity. So fluid viscosity is the cause for this pressure drop, and this type of pressure drop, which is due to fluid viscosity, is called major loss. It's a terminology that you have to learn because when you're dealing with pressure, calculating pressure drop, we distinguish between two types of losses. One of them is due to fluid friction, and we call it major loss. Okay, so it's a definition that I'm introducing. It's something that even your mock exam addresses. Major loss is pressure drop due to fluid viscous forces. If we introduce a major loss, then we also have to think that there would be something called a minor loss, which we'll come to. Okay. Okay. So if we take we take this expression here, okay, we can write delta P over V bar squared equal to 32 mu times L by D squared. Okay, it doesn't look in a very convenient form, but when we did pipe flow analysis or scaling analysis of pipe flow, what did we normalize delta P by? When we said delta P is a function of viscosity, density, velocity, length, and diameter. Do you remember the normalization? This was normalized as delta P divided by rho V squared equal to a function of Reynolds number, which is defined as rho Vd over Q, and then L over D. So we, in scaling analysis in module 6, we only did the derivation of these non-dimensional numbers. For the first time, we are seeing a formula. We are going to express this formula in this form. To do that, what do we need to do? I'm missing a density here. So I'm going to write delta P over rho V squared equal to 32 mu. Okay. And I have to again divide by rho. And I'm going to separate a diameter from here, write it over here, and then I have L over D. Sorry, I don't know how I got V squared. I should have had V. So I have delta P divided by rho V equal to 32 mu rho D. That looks like nonsense, except if I multiply by V, divide by V, I will have delta P over rho V squared equal to 32 mu rho V D times L over D. That looks like something. Can we recognize what is mu divided by rho V D? What is mu divided by rho V D? Inverse of Reynolds number. So this is like writing 32 divided by Reynolds number times L over D. So we have now brought this to a form where delta P over rho V squared equal to 32 divided by Reynolds number multiplied by L over D. I'm going to ask two questions here. Okay. Major loss. That is delta P due to fluid friction or fluid friction is given by delta P over rho V bar squared equal to 32 divided by Reynolds number times L over D. So now question for you, if I ask you to calculate pressure drop across a section of pipe, what do you first need to know about that flow? Based on this equation, what all quantities are needed to calculate delta P?
The diameter and well, I mean, you need all 5 of those. So the first one you would want to do is
So you're basically saying that you will take this to the other side, 32 divided by Reynolds number multiplied by L over D multiplied by rho V squared. So to know delta P, you need to know Reynolds number, you need to know length expressed in multiples of the diameter, and you need to know density, and you need to know the average velocity to compute this. Right? So there's a reason why this type of loss is called a major loss. If there is a pressure drop in a flow system, almost 80 to 90% will be due to friction. That is, what is the flow system? If you have seen your dishwasher or your washing machine or your refrigerator, what is it made of? How does it transport fluid or gas? Through tubes, right? A flow system or a fluid system is nothing but a bunch of tubes or pipes that are connected together with fittings like elbows, T, cross, kind of fittings that basically bring tubes together. Or they might have cross-section changes from with a nozzle or an expansion valve or something. Have you seen any of these? Like a tube, you've seen a tube, right? What is an elbow? You have used some of these in the shop. These are 90-degree bends, right? This is an elbow. Okay. What is a T? A T basically is a flow splitter where one flow comes in one way, splits into two, or flow comes in two ways and combines into one. Or you can have a cross. Or you can have a cross. Or you can have a nozzle where there is a reduction in cross section. Or you can have an expansion valve, which is basically nozzle with the backward flow direction. Expansion valve. Or actually the word is diffuser. Or you can have what is called as a orifice where the flow comes through and then has to expand it. Okay, I'm making a very important distinction, so please look up, take a moment, take a pause. The loss in pressure due to fluid friction is called major loss, where nothing extraordinary happens, the fluid just flows along the pipe, the friction acts at the wall, and that force or that viscous effects propagates inwards and causes losses in the whole flow. That type of loss is called major loss. And as you can see from here, major loss for a fully developed pipe flow, that is for fully developed laminar, meaning Reynolds number is less than 2300, pipe flow is given as this formula. It scales inversely as Reynolds number, which means, what does that mean? It scales inversely as Reynolds number. If Reynolds number is lower, delta P goes up or goes down? Up, right? Then you wouldn't say that, you would point your fingers up. So what does that mean? The slower the flow is, the greater the pressure drop in laminar region. Not only that, it also scales with velocity squared. And of course, Reynolds number also depends on velocity, and this depends on velocity squared, which means the delta P, you're going to answer these for me. What is the dependence of delta P on velocity? There is a inverse Reynolds number, which means there is rho Vd over mu, and then there is a velocity squared, which means it is velocity to the first power. Delta P scales with velocity. How does delta P scale with diameter?
I think a word for the course of the diameter velocity is like this.
That is true, but by what factor? Meaning, if you think of the original equation Q, which is V divided by, sorry, if you take Q, is pi over 128 mu delta P over L times D to the fourth. So if you just keep in terms of flow rate, this implies delta P scales as 1 over diameter to the fourth. What is the implication? If you double the diameter, if you make D2 equals 2 times D1, what is the implication of that for the pressure drop? How many times does that increase the pressure drop? So take this relation. Delta P 1 scales as 1 over D1 to the fourth. Delta P2 scales as 1 over D2 to the fourth. So delta P2 divided by delta P1 would be 1 over D2 to the fourth times D1 to the fourth. If D2 over D1 is twice, that means this is 1 by 2 to the power 4 or 1 by 16, which means delta P2 is 16 times delta P1. You double the diameter, you get 16 times more pressure drop. So the pressure drop with a smaller tube will be more or a larger tube will be more. A 1-inch tube or a 2-inch tube, which will have larger pressure drop if everything else is the same, including flow rate. Did you say larger tube, the 2-inch tube?
Yeah.
What, any other responses? If you have two tubes, 1 inch and 2 inches, considering flow rate, viscosity, length are all the same, which tube will have higher pressure drop? Do this math. Delta P2 over delta P1 is 1 inch divided by 2 inch to the fourth, which is like saying 1 over 16, or the pressure drop in the second case will be 16 times whatever the pressure drop is in the first case. This will always have, or meaning the smaller tube will always have higher pressure drop, not the other way. Always the smaller tube will have higher pressure drop than a larger tube for the same flow rate and same fluid and same length. Okay, so this is coming exactly from this relation where you get the relationship between pressure drop, length, diameter, and flow rate. Think of this question. What is the proportionality between pressure drop and flow rate from this equation? To the first power, right? Just scales us. Delta V scales us. If you double the flow rate, how much will the pressure drop increase? Twice. If you double the length, how much will the pressure drop increase? So delta P proportional to L to the power 1. If you double the length, how much will the pressure drop increase? Double the pressure drop, right? Among these variables, diameter is the most sensitive. If you halve the diameter, you will get 16 times more pressure drop. That's the implication. Okay. So what you need to remember, or what you need to be able to use for the exam, is this relation and all the proportionalities that come with it. Okay. Need to be able to calculate scaling in these quantities. It can be both ways. That is, you can ask, if I keep the same pump, that is, if I keep the same pressure drop and half the length, how much will my flow rate increase? Flow rate Q, if you keep everything else constant, scales as 1 over L. If you keep the same pressure drop and but half the length, you will get double the flow rate. You should be able to do these type of reasoning problems using this equation. Question?
With the pressure drop difference, shouldn't it be pressure 1/16 instead of 16 times the pressure of 1?
Oh, yeah. That is, when you go from 1 to 2, pressure will decrease. So this is 1/16. If you want to write delta P1, that will be 16 times delta P2. That is my point being, the smaller diameter will always have the higher pressure drop. Okay. So major loss is always the pressure drop due to fluid friction. It depends on these quantities, Reynolds number, the length, and rho v squared. Okay, when we express this, we write it as delta P over rho v squared equal to, delta P equal to a friction factor F times rho v squared. We call this F friction factor. It's a factor. What is the unit of this quantity here? 32 by Reynolds number times L by D. What is the unit of that quantity? Are you okay? Tired? What is the unit of F? Reynolds number unitless, L by D unitless, 32 is a pure number, which will give us F is dimensionless. Okay, so I'm going to make a table here, major loss. Okay. Always delta P is equal to F times rho V squared. That's the equation we are going to use both for major and minor loss. For laminar, for delta P equal to F times rho V squared. Okay, for fully developed laminar flow, the major loss, friction factor F, can I write this as 32 divided by RE times L divided by D. That is, instead of calling this to be only valid for friction for laminar flow, what I'm saying is I'm generalizing it into an F and say F happens to be 32 divided by RE times L by D for laminar flow. Then you will ask the question, what about the value of F for turbulent flow? Can I look up F for turbulent flow, or can I do the math for turbulent flow? Can I? That is the question that you want to answer. Okay. And the math is very complicated, or to know F for turbulent flow is not easy. So what we did was to prepare a lookup chart called Moody chart, where you can look up F as a function of Reynolds number as well as the pipe roughness, okay, as well as pipe roughness. This is F times L by D times rho V squared. L by D is absorbed into here, so F is only 32 divided by RE. So this 32 divided by RE also assumes a smooth or rough pipes. Whereas this Moody chart, which I'm going to bring up here, is a tabulation of experimental data that summarizes F for a wide range of Reynolds number and epsilon over D, or this epsilon is nothing but pipe roughness. Meaning the surface features on a pipe, the average height of those features is what we call epsilon. If you have your text with you, you can look up figure 8.20 or page 431. Okay, I'm going to bring it up here. So please look up here. This is a plot of the friction factor F as a function of the Reynolds number Re and the pipe roughness epsilon, okay, which is on the right here, little hard to see over here. Okay, so if you look at this this straight line here, that is the friction factor expression for laminar flow, which is 32 divided by Reynolds number. We got that just from the formula for laminar flow. So this you can see falls linearly with Reynolds number, and the transition point is around 2300. So until 2300, this curve or the analytic formula 32 divided by Re can be exactly used to compute friction factor. The implication is, if the flow is laminar, it doesn't matter what your pipe roughness is, whatever disturbances that the roughness will introduce will get damped out by the viscous action. Okay. If you are beyond 2300,